Welcome back to G Fun Facts Online. Today, we are abandoning the shallow end of the pool and diving straight into the deepest trenches of modern physics. We are going to talk about a discovery that effectively traps the ghost of Albert Einstein inside a microchip. We are talking about gravitational mimicry. This is a story about how researchers have managed to make electron beams bend like starlight, bridging the century-long gap between quantum mechanics and general relativity, not with a new theory of everything, but with a brilliant material hack. To understand why this is such a monumental shift, we have to set the stage with the two pillars of physics that usually refuse to speak to each other. On one side, you have quantum mechanics, which governs the chaotic, probabilistic dance of subatomic particles like electrons. It is a world of uncertainty, wave functions, and discrete energy levels. On the other side, you have general relativity, the majestic deterministic theory of gravity proposed by Einstein. In Einstein's world, mass tells space how to curve, and space tells matter how to move. For over 100 years, these two worlds have remained estranged. To study gravity, you looked at stars and black holes. To study electrons, you looked at microscopes and silicon chips. But in late 2024 and throughout 2025, that separation began to dissolve. Laboratories at the University of Geneva and Tohoku University have discovered that within the atomic lattices of specific advanced materials, the geometry of quantum states can be twisted. They found that they could create a fictitious gravitational field. In this distorted quantum landscape, electrons stop moving in straight lines and start curving, mimicking the way light bends around a black hole. This isn't just a metaphor, it is a measurable, controllable physical reality. Let's rewind to 1919 to really grasp the gravity, pun intended, of this situation. Sir Arthur Eddington traveled to the island of Principe to photograph a solar eclipse. He needed to prove Einstein's wild prediction that the sun's gravity would warp the fabric of space itself, causing starlight from distant clusters to bend as it passed by. Eddington confirmed it, and gravitational lensing became a cornerstone of astrophysics. However, solid-state physicists, the people designing the materials for your phone and computer, largely ignored this. They assumed that electrons in a solid moved through a flat, boring Euclidean background. They thought electrons might bump into atoms, but the space itself was considered uncurved. That assumption is now dead. A team led by Giacomo Sala and Andrea Caviglia at the University of Geneva uncovered a hidden geometry in quantum materials. They realized that the mathematical rules governing electrons in certain crystals are eerily identical to the metric tensors Einstein used to describe curved spacetime. When an electron moves through these materials, it does not feel a flat grid. It feels a warped, twisted landscape. It follows a curve not because a force is pushing it, but because the straightest line, or the geodesic, in that quantum geometry is a curve. So, how do you build a universe on a chip? The magic happens at the interface of two specific oxides, lanthanum aluminate and strontium titanate. Individually, these materials are insulators. They are boring, but sandwich them together with atomic precision, and a two-dimensional electron gas forms at the boundary, allowing electricity to flow. But the Geneva team did something very specific. They cut the crystals along the 1-1-1 direction. In crystallography, the angle of the slice determines the atomic arrangement. This specific angle creates a hexagonal, honeycomb-like symmetry on the surface. It is difficult to work with, but it is rich in exotic physics. In this specific interface, the electrons experience something called spin-momentum locking. Imagine an electron not just as a charged ball, but as a spinning top. In a normal wire, the spin and the direction of motion are independent. But here, they are locked. If the electron moves forward, it spins clockwise. If it moves backward, it spins counterclockwise. This rigid coupling is the first step toward creating a curved environment. Now, we have to get into the engine room of this discovery, the quantum geometric tensor. This is the deep math that makes the magic possible. Since the 1980s, physicists have known that quantum wave functions have a shape. This shape is described by the quantum geometric tensor, which has two parts. The first part is the imaginary part, known as Berry curvature. You might have heard of this. It acts like a magnetic field in momentum space and is responsible for the quantum Hall effect. It bends electrons, but it does so like magnetism, perpendicular to motion. The second part, the real part, is called the quantum metric. This is the sibling that was ignored for decades. The quantum metric measures the distance between quantum states. If the metric is flat, all states are equidistant. If it is curved, the distance changes as the electron moves. Crucially, this metric enters the electron's equations of motion exactly how the gravitational metric enters Einstein's equations. The Geneva team proved that in their lanthanum aluminate and strontium titanate interface, this quantum metric is not zero, it is strong. When they applied an external magnetic field, the interaction with the quantum metric caused the electrons to deviate from their path in a nonlinear way. They weren't just being pushed by the Lorentz force of standard magnetism, they were surfing the gravity of the crystal. But how do you actually see this? You cannot use a telescope. The researchers used a technique called the nonlinear Hall effect. In a standard linear Hall effect, you send current north, apply a magnetic field, and voltage appears east. In this nonlinear version, the voltage response scales with the square of the current or magnetic field in complex ways. The team observed a specific type of nonlinear resistance that could only be explained by the quantum metric. By carefully mapping these distortions, they effectively mapped the shape of the quantum space. It was the solid-state equivalent of measuring the deflection of starlight, but instead of using a telescope during an eclipse, they used voltmeters and cryostats cooling the chip to near absolute zero. While the Geneva team was bending electrons, a group at Tohoku University in Japan, led by Kyoko Kitamura, was achieving a parallel feat with light itself using photonic crystals. These are materials structured with a periodic grid to control light flow. By deliberately distorting the lattice, stretching the grid spacing gradually, they created an effective gravity for terahertz waves. Just as a black hole stretches spacetime, the distorted lattice changed the refractive index, causing light beams to curve and perform U-turns around a center of attraction that didn't physically exist. This is called pseudogravity, and it confirms that the principle is universal. Whether it is electrons or photons, if you engineer the geometry, you can mimic gravity. So why does any of this matter to you? The applications are staggering. First, let's look at the concept of the lossless switch. Gravity is a conservative force. A planet orbiting a star does not lose energy to friction against the vacuum of space. If we can make electrons move via these gravitational quantum pathways, we might bypass the scattering and resistance that generates heat in modern electronics. This is a potential route to dissipationless electronics, chips that don't get hot and consume a fraction of the energy. Then there's the future of communication, 6G. We are currently moving towards 6G networks, which will rely on terahertz waves. These waves are notoriously difficult to control because they pass through most lenses without bending much. But with gravitational lenses built into the chip, we could steer these beams with perfect precision, enabling ultra-fast wireless data transfer. We also have the field of quantum sensing. Because the quantum metric is incredibly sensitive to the shape of the electron state, it can be used as a sensor. Any tiny change in the magnetic environment or the material's stress alters the curvature. Devices built on this could detect minute magnetic fields, useful for medical imaging or geological scanning. And perhaps most excitingly for the theorists, we now have the desktop black hole. We cannot fly to a black hole to test what happens to quantum information near an event horizon. But if we can create a mathematical duplicate of a black hole's curvature inside a crystal, we can shoot electron beams at it and see what happens. We can test theories of Hawking radiation or the information paradox using a small crystal sample instead of a billion-dollar space telescope. This discovery brings us full circle to a dream Albert Einstein held but never realized: the geometrization of physics. He believed that forces were just illusions caused by geometry. He proved it for gravity, but failed to prove it for electromagnetism. The discovery of the quantum metric in solids suggests he was right in spirit. Even in the quantum world, geometry rules. The forces we measure in these chips are actually just electrons following the curves of a hidden landscape. We are entering a time where we no longer just design circuits with lines of copper. We are designing microscopic universes, regions of curved spacetime where electrons orbit, dive, and escape like comets in a solar system. Gravitational mimicry is more than a clever trick. It is the unification of the very large and the very small on a silicon wafer. From the event horizon of a black hole to the atomic lattice of strontium titanate, the universe speaks the language of geometry. And, for the first time, we have learned how to speak back. That wraps up this deep dive on G Fun Facts Online. If you enjoyed this journey into the quantum realm, make sure to stay tuned for our next episode.